Today's topic is experimental verification of Maxwell's speed distribution law. Maxwell's speed distribution law gives number of molecules per unit volume in speed range C to C plus dc by this formula. If n is the number of molecules per unit volume, then dn number of molecules per unit volume in speed range C to C plus dc is equal to 4 pi n m upon 2 pi kt to the power 3 by 2 c square e to the power minus mc square upon 2 kt into dc. So according to Maxwell's speed distribution law, number of molecules per unit volume in a given range of speed C to C plus dc is given by this formula. dn equal to 4 pi n m upon 2 pi kt to the power 3 by 2 c square e to the power minus mc square upon 2 kt dc. Here in this exponential we can consider it as e to the power minus half mc square. It is the kinetic energy of one molecule, half mv square. So if we consider half mc square in numerator, then in denominator it is kt. kt is thermal energy, T is absolute temperature, K is Boltzmann's constant. So exponential is dimensionless. Here we have e to the power minus, in numerator we have kinetic energy half mc square, and in denominator we have kt thermal energy. With this, the volume element in the speed range C to C plus dc is 4 pi c square dc. So we have this factor 4 pi c square dc. Now experimental verification of Maxwell's speed distribution law. We can verify Maxwell's speed distribution law by Lambert's apparatus shown in this figure. This is Lambert's apparatus used for experimental verification of Maxwell's speed distribution law. O is oven in which mercury Hg is filled at high temperature. This is the oven. O is oven. Mercury Hg is filled inside it at high temperature, so that we have molecules of mercury inside this oven O. S is a small pinhole through which these molecules of mercury comes out and moves in different directions. Molecular beam of mercury atoms obtained from pinhole S of oven O passes through the collimating slit so that a narrow beam is obtained. S is pinhole through which mercury atoms comes out and moves in different directions. These are allowed to fall on this combination of two parallel slits S1 and S2. And we found a fine collimated beam of mercury atoms by using these two slits, parallel slits S1 and S2. So after passing through these two slits, we found a fine collimated beam of mercury atoms. A narrow beam is obtained, narrow beam of mercury atoms. Since number of molecules in diffused gas passing out from pinhole S is small, their interaction in beam may be assumed as negligible. Number of molecules of mercury passing out from small pinhole S is very small. We can assume the interaction between these mercury molecules as negligible. In this fine beam of mercury molecules, we assume that there is no interaction between molecules of mercury. No force is acting between these molecules because they are in very small numbers. Such beam is known as molecular beam. D1 and D2 are two disks attached with a axle. These are two disks D1 and D2 attached to an axle. Slots in disk D1 and D2 are made in such a way that the angular separation is theta, approximately 2 degree. D1 and D2, these are two disks attached with same axle. Two slots are made in these disks at angular separation theta, which is approximately 2 degree. And this molecular fine beam of mercury molecules is allowed to fall on first slot of disk D1, and then it passes through slot of disk D2 and then reaches to the detector, which counts the number of molecules. Now the number of molecules which passes from the two slots of disk D1 and D2 can be found by this condition that only those molecules can pass through the slot of disk D2 which are coming from slot of disk D1, which have speed c such that the time taken by these molecules from D1 to D2, this distance is small d, so time taken in traveling a distance d will be equal to the time taken by the slot of disk D2 to rotate by angle theta. Only those molecules can pass from these two slots of two disks D1 and D2. Molecular beam is allowed to incident on disk D1. Disk D1 and D2 are rotated by rotating axle with angular velocity omega. It is not W, it is omega, angular velocity by which these two disks are rotated by rotating the axle. From those molecules which pass through slot of disk D1, only those molecules passed through slot of disk D2 whose speed c is such that the time taken by molecules in traveling a distance d between two disks, it is not alpha, it is distance d. D, small d, is the distance between two disks D1 and D2. So time taken by molecules in traveling a distance d between two disks will be equal to time taken by disk D2 in rotating by an angle theta. Time taken by molecules in traveling a distance d is d upon c. Speed is distance upon time. This gives the time equal to distance upon speed. It is d upon c. And time taken to rotate an angle theta by angular velocity omega, it is theta upon omega. Angular velocity omega is angle upon time, so time is angle upon angular velocity. This gives the speed c equal to omega d upon theta. So molecules of this speed will pass through these two slots of two disks D1 and D2 and reach to detector where they are counted. Molecules of speed c equal to omega d upon theta are detected by a detector by changing angular velocity of disk omega. Number of molecules with different speeds are detected by the detector. If we change angular speed omega, c will be changed. So by changing omega, c is changed and we detect the molecules of different speed c. By changing angular velocity omega, number of molecules with different speeds are detected by the detector, and this experimental value agrees with Maxwell's speed distribution law. Now, using Maxwell's speed distribution law, we find three speeds. First is most probable speed, second is average speed or mean speed, and third is root mean square speed. Maxwell's speed distribution law is given by this formula: dn equal to 4 pi n m upon 2 pi kt to the power 3 by 2 c square e to the power minus mc square upon 2 kt dc. N is number of molecules per unit volume. Then dn number of molecules per unit volume in the speed range C to C plus dc is given by this formula according to Maxwell's speed distribution law. Now from this speed distribution law we find first most probable speed for which probability is maximum, speed for which number of particles are maximum. Probability of a molecule having speed in the range between C to C plus dc is given by dn upon n. N is the total number of molecules per unit volume and dn is number of molecules per unit volume in the speed range C to C plus dc. So probability that a molecule have speed in this range C to C plus dc is given by dn upon n, and dn upon n is equal to 4 pi m upon 2 pi kt to the power 3 by 2 c square e to the power minus mc square upon 2 kt dc. We write this probability dn upon n as fcdc. fcdc is the probability that a molecule have speed in this given range C to C plus dc. Most probable speed, we write it by Cp. P is for most probable speed. Cp, most probable speed, is the speed for which number of particles are maximum or for which probability Fc is maximum. So for most probable speed, probability Fc must be maximum, so its differentiation must be equal to 0. According to condition of maxima and minima, a quantity will be maximum or minimum if its differentiation is 0. So probability Fc to be maximum, its differentiation with respect to C will be equal to 0. So we have the condition for maximum Fc, dFc upon dc equal to 0. d upon dc, put the value of Fc, which is 4 pi m upon 2 pi kt to the power 3 by 2 c square e to the power minus mc square upon 2 kt. We have to differentiate this quantity inside the bracket with respect to C. 4 pi m upon 2 pi kt to the power 3 by 2 is constant. Factor C appears in these two terms. First is C square and second is e to the power minus mc square upon 2 kt. So we differentiate it by using the formula of first function and second function. First function is c square, second function is e to the power minus mc square upon 2 kt. So using the formula first function differentiation of second plus second function differentiation of first, we get c square, it is first function, differentiation of second, differentiation of e to the power minus mc square upon 2 kt. Its differentiation is e to the power minus mc square upon 2 kt. And in exponential we have minus mc square upon 2 kt. Its differentiation with c will be minus m upon 2 kt, which is with c square, and differentiation of c square is 2c. So first function is c square and differentiation of second is minus m upon 2 kt into 2c into e to the power minus mc square upon 2 kt. Then plus second function, which is e to the power minus mc square upon 2 kt into differentiation of first. Differentiation of first, differentiation of c square is 2c and it is equal to 0. minus 2c e to the power minus mc square upon 2kt is taken as common. Two c e to the power minus mc square upon 2kt is taken as common. Remove this minus sign. Then inside the bracket the remaining term is minus mc square upon 2kt plus 1 equal to 0. So the quantity inside the bracket must be equal to 0, or mc square upon 2kt will be equal to 1. This gives the value of c square equal to 2kt upon m, or c equal to under root 2kt upon m. This value of c is equal to cp. It is the most probable speed. So we find the most probable speed cp equal to under root 2kt upon m. Second is average speed or mean speed. C is the speed and its average is found by this method. Average of C is integral C dn upon integral dn. We write this average speed or mean speed by Cm. M is for mean. So mean speed, mean value of C is integral C dn upon integral dn, and we put the value of dn by using Maxwell's speed distribution law in numerator, and in denominator integral dn will be equal to n. So it becomes 1 upon n integral C, and it is the value of dn, which is 4 pi n m upon 2 pi kt to the power 3 by 2 c square e to the power minus mc square upon 2 kt dc, and limit is taken as 0 to infinity. Speed of molecules may vary from 0 to infinity. N is cancelled out. It is in numerator and it is in denominator also. 4 pi m upon 2 pi kt to the power 3 by 2 is taken outside the integral, and then we have integral c cube e to the power minus mc square upon 2 kt dc. This becomes equal to 4 pi m upon 2 pi kt to the power 3 by 2, and value of this standard integral is 1 upon 2m square upon 4k square t square. Value of this standard integral is 1 upon 2 into, in denominator with 2 we have square of the term in exponential with minus c square. In exponential with minus c square we have m upon 2 kt, and its square is m square upon 4k square t square. Value of this standard integral is 1 upon 2 m square upon 4k square t square, and this gives the mean value of Cm equal to root 8 kt upon pi m. And now we will find root mean square speed. Root mean square speed, we write it as CRMS. RMS is for root mean square. So we first square C. Square of C is C square. Then we take its mean. Mean of C square is integral C square dn upon integral dn, and we then take its root. This gives the value of root mean square speed CRMS equal to root integral c square dn upon integral dn. In denominator, integral dn is n, and in numerator we put the value of dn by using Maxwell's speed distribution law. So this gives integral dn is n, it is inside the under root, and integral c square, and this is the value of dn. This whole term is inside the under root. So correct this, put under root. This entire term is inside the under root. N is cancelled out, it is in numerator and denominator. 4 pi m upon 2 pi kt to the power 3 by 2 is taken outside the integral, and then inside the integral we have c cube e to the power minus mc square upon 2 kt dc. It is c4, it is not c cube, it is c4. It is c4 e to the power minus mc square upon 2 kt, and then we put the value of this standard integral c4 e to the power minus mc square upon 2 kt dc, and then this value of CRMS will comes out to be equal to root 3 kt upon m. So correct this result. CRMS, it is not equal to root 8 kt upon pi m, it is under root 3 kt upon m. We can find the ratio of these two speeds, Cp, Cm, CRMS. Inside the integral we have kt upon m, it is cancelled out, and then the ratio of these three speeds Cp, Cm, CRMS will be 1 upon 1.141 upon 1.04. So ratio of these three speeds Cp, Cm and CRMS, it is 1 upon 1.141 upon 1.228. So correct this, it is 1 upon 1.128 and then upon 1.224. Correct this. 1, it is 1 upon 1.128 upon 1.224. Correct this here also. CRMS under root is all these terms in right hand side, and then inside this integral we have c4 e to the power minus mc square upon 2 kt dc, and if we put the value of this standard integral c4 e to the power minus mc square upon 2 kt, under root is already there, then the final result here for CRMS, it is not root kt upon pi m, it is root 3 kt upon m. This CRMS, which is root 3 kt upon m, if we multiply by capital N, total number of molecules, If we take 1 mole, it will becomes equal to Avogadro number. Multiply and divide by capital N. Then Nk will becomes equal to R, universal gas constant, and capital N into small m, it is capital M, it is molecular weight. So if we consider 1 mole gas, capital N is Avogadro number, multiply and divide in numerator and denominator, multiply by N, then Nk is equal to R, universal gas constant, and Nm, m is the mass of one molecule, then Nm is the mass of 1 mole gas, it is molecular weight, capital M. So CRMS, which is under root 3 kT upon m, it will becomes equal to under root 3 RT upon m.